Hello, and welcome to our webinar, Transition to the Cloud Without Compromises. My name is Josh Verrill, and I will be moderating today's webinar. I'm joined here by Nick Trevelyan-Jones, a Senior SaaS Architect at NewODB, and Simon Henman, a Senior Product Manager, Banking Performance at Terminus. In this webinar, Nick and Simon will cover how to meet customer demands for application availability and agility, how to migrate to the cloud without re-architecting every application, how to use distributed SQL databases as your on-ramp to the cloud, and how to lower TCO and improve performance within your business-critical applications. At the end, we'll open it up for Q&A. Before we begin today's presentation, I'd like to review a few logistics. Our webinar will last about 45 minutes. The webinar will be recorded, and the video and slides will be made available for replay. Attendees will be muted during the call. However, you may submit questions at any time during the presentation using the questions box in the GoToWebinar control panel. So with that, I'll turn it over to Nick. Nick?
Josh, thank you very much. So hello, everybody. As Josh said, I'm a Senior SaaS Architect with NewODB. I've been working with databases of various types for the vast majority of my career, including object databases and RDF databases. And Simon.
Hi, I'm Simon Henman. I've been working for Terminus in the performance space for around 12 to 14 years, but approaching 20 years in the banking space with the software itself.
Simon, thank you very much. So I have here an outline of the Terminus's core banking system. As you can see, it's a very powerful system with a number of components. For banking and for a system this powerful, it needs a high availability solution. The back-end systems there, the Terminus transact and payments hubs, have various features for high availability, including using message queues to have a retry and failover, etc. I'll leave it to Simon to discuss more about the Terminus product itself. If we look at the bottom row of this slide, we can see a significant range of deployment possibilities, and this is going to provide quite a challenge. One solution is to use the ideal database in each of these, or the proprietary database on each of these platforms, but that then obviously has a very high cost in development and maintenance and are actually running the different databases. So a very attractive solution would be a database that is platform neutral and can be run in any and all of these environments as easily as all the others, and that would therefore simplify the development and deployment costs and the running costs for Terminus and the people actually running these products. So looking at the options in databases, on the left here I have the traditional relational database, and on the right the NewODB distributed database. So the main point to highlight is that the traditional database is monolithic. All of its processing occurs on a single host with its attached storage, and the back-end application servers connect to that database. So to have high availability on this type of database, basically the model is run multiple copies of my database in different locations and then organize some technology to try and keep those in sync. And technologies are out there that do this, but they are complex and expensive, and they have a runtime maintenance issue in terms of people keeping these things running. The NewODB architecture is entirely different. So basically, we've separated out the different aspects of the database processing, and these can be deployed in multiple processes on different hosts in the system. So not just running multiple copies of the database, but the NewODB approach is much more take my single database and arrange to run different parts of it on different nodes and let them coordinate as a single database. So this also fits really well with the cloud and container deployment models. So with NewODB, you can get to the model of a single process in a single container, rather than with a monolithic database where you would be looking at normally multiple processes in the container and effectively fairly big, heavy containers, struggling to try and actually separate this database up into smaller components. So if you now have your NewODB database running in a containerized environment in those containers effectively natively, now you can manage it with the container management systems such as Kubernetes or OpenShift, etc. So the issue with the big issue that we're going to see with the relational database is that if we have this high availability model of multiple copies of the database, then to deal with a failover event, I'm effectively moving all my processing from one database to another, and there is a time period. The RTO is not zero on that event. With NewADB, we can have multiple copies of the different processing nodes running simultaneously, and a failover event is simply some nodes have gone away, the hardware is no longer there, the network connection is gone, but the other nodes are continuing running. So the active-active model that people talk about, although with a distributed database, active-active is a bit more involved, a bit more interesting. So NewADB is not just therefore a distributed database. As I said, we've actually separated out the different processing, and these can run in individual processes, now individual containers, spread around on a cluster. So the two types that we're looking at here in this diagram on the right of this slide are the TEs, which are the transaction engines, which perform all of the SQL processing and the actual transaction demarcation. And then the SMs, the storage managers, which actually do the persistence. And each of these colored circles here can be a separate process on a separate node running in its own container. So the database has been separated into much smaller components than just, I've got one database here and one database over there. In addition to that, NewADB gives you high availability out of the box. As you pointed out, I have multiple copies of these TEs and multiple copies of these SMs. So if one or more of those TEs go away, so long as I still have sufficient, the database continues running with no loss of service at all. So this is RTO 0. And we will look at the benefits you get from that. So the NewADB goals, if we want to summarize them, are distributed so that we can take advantage of increased hardware. So I can add CPU to my database, I can add memory to my database simply by adding more nodes, running up more containers. So I can scale out rather than just scaling up, which is the monolithic approach. And so I have elastic scale, I can increase the number of nodes and increase the throughput the database can sustain, and high availability. By having multiple copies of these processes, I have no single point of failure within the database. But there's more to it than that. So that's the basis, and even that is a difficult enough achievement. There aren't that many distributed databases in the market space. But basically, we also have added full ACID transactional guarantees. So we ensure that a transaction is not acknowledged back to the client until we know that we have multiple copies of that data on disk. And it is a full SQL database. So it's not just a distributed storage layer with some level of SQL put on top. It is centrally in its core a SQL database. The SQL processing is happening all in the TEs. So those transaction engines are the transaction locking and all the SQL processing, and they are caching all their data locally. So they are running their queries directly against data that is local to them in their own RAM. So scaling out this database is for, if I need to add more memory or more CPU for doing SQL processing, I can simply start up more TEs, obviously on extra hardware, and that will give me greater throughput. In a containerized, such as the Kubernetes managed environment, that is as simple as a single command, just saying, kubectl scale TE pod minus replicas equals 6, 10, whatever I need the new number to be. So a single command to grow the database, to grow its processing capabilities. And clearly, that kind of command can be automated in a cloud elastic component. So we can put in the thresholds to say on this kind of event, it may be on CPU hitting certain values or message queues and getting to a certain size, we start scaling the database up automatically. So in the kind of SaaS environment where we're looking at a self-managed database or an fully automated database, this kind of scaling and control is easily automated with off-the-shelf components like Kubernetes. So the storage managers are very different. And one of the big benefits that we get in NeoDB is that we've taken the distinct problems of storage away from the other issues of SQL and transaction and caching and all of that. So we can deal with SMs and their unique needs entirely separately. So the SMs also provide high availability in terms of the fact that if I have multiple SMs and one of them goes away, a node gets lost, the disk, the actual hardware disk has problems, etc., the other SMs continue processing, and the database again has an RTO failover event. It continues processing, and then a new SM can be started later. But the other thing that SMs provide, which TEs don't, is data redundancy. So they're storing data on disk. And so having multiple SMs, I'm now getting multiple copies. With a distributed high available database such as NeoDB, you don't tend to use that feature very often. Really, the feature gets used if you shut the database down completely and cold start it. But you still do need to have that guarantee that if for whatever reason we have to shut the database down and we restart it, we must know that we have a guarantee that we have the most recent committed transaction on disk somewhere, and that we can start that database without losing transactions. So that's the second guarantee that the distributed storage managers of NeoDB gives us. So think of the SMs in terms of a RAID array with disks. And so each SM is, well, the SMs form as a group, form the RAID controller, and then each SM is connecting to disk, which is the actual physical storage, which are these disks that you slide in and out of your RAID. So if we lost a disk, the node with the storage, or the even an entire availability zone in the cloud goes away, and that storage is just no longer available, then the SM associated with it shuts itself down, saying I've got no storage. We can, once the hardware problem has been resolved, we start the SM up. And so now the SM, the newly started SM, talks to the others and it says, okay, what have I missed? And so basically, you've plugged your new disk into the RAID array and you've got the orange light flashing as it says, well, I'm plugged in and I'm good, but I'm still synchronizing my data. So the NeoDB SM layer automatically performs that synchronization. And when the newly started SM is up to date with the state of the database, its light goes green and it can now start processing, adding to the processing of the database. So the database is self-healing. If we lose some nodes, either Ts or SMs, then a Kubernetes can start replacements, and those replacements will automatically synchronize with the active state of the database and then put themselves online and continue processing, adding to the throughput of the database. So why does distributed matter? I've given you a nice kind of overview and a hint as to these advantages, so I'll kind of sum them up on a single slide now. So basically, being able to add throughput, being able to cope with growing business. I mean, we all are in business to make a profit and to do better. So growth is a good thing. We don't want to be limited by our infrastructure to say, well, we can't be more successful than X because our database can't go bigger than X. So to quote someone from many decades ago, Admiral Grace Hopper, who talked about scalability some 50, 60 years ago, basically when they were dragging logs along rivers, and they had a tree that was too big, they didn't try and breed a bigger ox. They just hooked 2 oxen up to the cart and they scaled out rather than scaling up. And so the distributed database is now fulfilling that kind of promise in one of the most complex areas of computing, which is distributed storage. So basically, with a monolithic database, you just have to keep getting a bigger machine. And so at any point in time, there is a ceiling on how much throughput you can deal with because your database can't grow any bigger. You also have the passive failover cost, that if I need to have the ability to failover very quickly, I have to have a second copy of this database running somewhere else, and I have to pay for that. So HA comes with a very high cost. It's basically doubling the hardware, and I have to have network, etc. And then there's usually a management component, day-to-day operational component, keeping that going. And at the end of the day, with all of that extra cost, we still have an RTO that's not zero. There will be a failover time. It's normally just in minutes, tens of minutes often, but it is still some period of time where we have no service from the database, and therefore our business is frozen. And for some businesses, that is, that will translate to millions of dollars a minute in terms of lost revenue. The distributed database, we're adding more machines to be able to increase capacity. As I said, you can add more RAM and CPU to an active running NeoDB database by adding more nodes and starting up TEs and possibly more SMs, but we'll be normally scaling up TEs much more than we scale up SMs. So basically, it isn't quite a limited scale, but we're looking at least 10x ability, scalability by being able to scale out. All the servers can be active, so your failover event now is just reduced performance until we've scaled back up, rather than a complete stop and having to pay for that by having a complete set of redundant processes that don't add to my throughput. So the overall cost is significantly lower, and I have an RTO 0 failover contract. So the scale out lowers our TCO, not just because we can actively use the HA components, but we can now fulfill the promise of only pay for what you're using when you actually use it. So you can scale a database out for large end of business processing, whether that's daily, monthly, yearly, or possibly all of those in different situations, and grow the database hardware size, handle that processing on the bigger database, and then scale back in. These things are never perfectly linear, but they certainly are far better than trying to just create a whole new database, copy all your data across, work on a bigger database, or always pay for the hardware that you need at the end of the month throughout the other 29 days of the month. And with NeoDB, we haven't had to provision as much hardware in the first place, but we also have the RTO 0 failovers in the event of hardware problems or problems in the cloud infrastructure. Single failures are handled, with the standard configuration out of the box. If you want to handle multiple failures, simultaneous failures, then you will need to have additional hardware available, but all of that hardware can be used in the normal day-to-day processing. So, all good to talk about it. You actually have to put it on machines and test it to make sure that it actually does what we claim. So this is one graph which has come from my colleague here, Simon, at Terminus. The blue line is NeoDB, and basically the scaling is close to linear. There has to be a tail off as you add more processors. There has to be communication between them, but you can see very clearly with the red line that it hits the limit of the box, and it goes no further than that. And we keep adding load, and that's fine, but there's no more resources in the database machine to actually handle those things simultaneously. So I'll let Simon talk much more about the performance and the benchmarking, etc. I think this graph speaks pretty much for itself. So I mentioned a bit that NeoDB is a very natural fit for containers. And with a bit more of that discussion, you can see that individual TEs and individual SMs would all sit in their own containers. So we sit much more natively in a containerized environment, which means that things like the microservices, using Kubernetes in your SaaS, you can now use Kubernetes to manage your NeoDB database as well. So we can be deployed on the same plane, control plane and data planes as the rest of your applications. With traditional databases, that's not the case. You can package a monolithic database into a container. Most customers that I've seen don't. They deploy their database externally to their managed cluster. So they're managing the database separately from the rest of their application stack and their Kubernetes and clusters. For many, that works. But if you're looking to go more toward a SaaS model where you have automation, having a database in a non-automated environment is going to make it very hard to automate its management. So we can not only leverage the management layer, but we can also leverage the isolation and the flexibility that containers give us. So NeoDB as a distributed database can run as a single database across multiple clusters, and those clusters could be in multiple availability zones in a cloud, or even if regulators are pushing the banks to do this, run a single database spreading across multiple different cloud providers. So if an entire cloud provider in your area, you know, Amazon goes down in all of East America, then if you have the other half of your database running in Google, you still have a database and you still have an RTO 0 failover. So to wrap up on that, the benefits with NeoDB from the distributed architecture, we can support the modern environments with containerization, microservices if you're going in that direction. We've separated the compute and the storage. We support active-active between all of the components, so you get a lower cost on your hardware, and you can grow this hardware either over time as your business grows, or to meet bursts in the traffic and in the workload. So we can scale out and then scale back in, so less elastic scale. And I've mentioned this, lent on this a number of times, is the automated operations. There are significant savings in terms of orders of magnitude in being able to automate these and not have people being paid by the day on a salary, caretaking each individual database or component. So NeoDB is architected on this future, this model for the future. So the database to build your future on, rather than trying to take your future component and microservices architecture and make that to an older monolithic database architecture. So high availability, failures in the underlying hardware or network, etc., will not stop the database. The database service continues. We have effectively RTO 0 failover events. Scalability, your database can grow over time and can grow and burst in and out as is needed. And flexibility, you can run your database in any of a range of deployments, and you can spread a single database over a range of those deployments. You can have part of a database on premises, part of the database in the cloud. You can burst out to the cloud. You could do 2 different cloud providers. There's a whole range of opportunities now available to enable a far more digital-only cloud-based enterprise. So with that, I'll hand over to Simon and let Simon talk more about what Terminus has been doing with NeoDB and the various benefits that they've been seeing.
Lovely. Thank you very much, Nick. A great overview. So building on the overview from Nick, I'd like to go through some of the performance space, some of the benchmarking that we've run, some of the benefits that Neo has brought Terminus as a banking solution, and some of the challenges and things that we have to deal with varying customers. So starting with customers have different requirements. Now, every single time you go to a car dealership, you have a chance of putting in different types of options. And that's exactly the same with a customer buying a banking solution. They may be a traditional banking solution running retail, but they may actually have loans. They may have corporate loans. They may only have corporate transactions. So we have very, very different requirements from every type of bank. And also within that, we have very different transaction types. Some banks are very, very pushy when it comes to digital online only. So you have a huge growth in digital inquiries, but not so many in actual banking updates. So the actual different transactions and volumes have SLAs across various architectures and geographies. For example, we have used a SEPA payment in our testing, which is a single European payment authority. And these have SLAs of minutes across the European network, and clearing has obviously its own SLAs. So we have these problems that we have to deal with. Every bank is bespoke and everything is very different. But there are other strange performance requirements. Everybody will try and log in and do something first thing in the morning and make sure that they can see their balance. Every time we get to payday, people will start transferring money, hopefully to their savings, but certainly to their loan payments and clearing some of their debts or otherwise. So we see large peaks in performance, and these peaks can be 5 times the operational workload. So how do we cater with these peaks, and what can we do for that? Well, NeoDB gives us the ability to have a distributed architecture, as Nick has already gone through, but I will be reiterating. And it also gives the ability to run in the cloud as an agnostic platform in any type of cloud. We've discussed the built-in DR and resilience, and I'll touch on that briefly towards the end of my presentation. But why NeoDB in the cloud? It gives you the ability to distribute your workload. It gives you built-in DR and performance. But across cloud is something that may be a regulation from the banking ombudsman in the region that you may have to have a backup solution. Thank you. Thanks. Okay, so we ran a mirror benchmark, and the mirror benchmark was to compare with any traditional RDBMS with NeoDB. Obviously, Terminus have been working very closely with NeoDB as their partnership has grown, and we want to actually make this our de facto standard for the cloud. So what we needed to do was compare it. In this particular test, we compared directly with Oracle, but as I say, this is not to speak about Oracle, this is to speak about RDBMS. This could be SQL Server, etc., 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 DB2. What the message you're getting here is that when you're running the NeoDB architecture, you get linear scalability. We push this up to 15 application servers and 3,000 TPS. But if you're running on a static 8-core database server, you will be effectively bottlenecked by the resources on the database itself, because the traditional monolithic, as it's been said, database RDBMS doesn't have the ability to distribute the workload and auto scale in any way. So running with just 8 cores on the database, we were able to run 3,000 TPS of transactions, banking transactions, and I'll explain the mix in a moment, across the network. With NeoDB, the reference was less than 6 cores as opposed to 32 when we ran our testing at the final. I'll come to that in a moment. Thank you. Okay, so we have to make sure that all banks are catered for in as many ways as possible when it comes to the benchmark. So for, as I said, every bank is bespoke and they all have their own transaction sets. But this is a retail mix of transactions based on more than 10 years of experience. These are the transactions that the banks will run all the time, heavy on inquiries, up to 60% inquiries, and then the rest of them are moving cash around, making money payments, transfers, and sometimes people will drill down into the details of their inquiries and their limits. Posting cover reservations, it's more of a banking term, so they're money transfers. So the real banking operations with a heavy lean on maybe 60% on the inquiry base. Thank you. So the conclusion we ran from running the two mirror testing, we ran this actually in the Azure cloud. So we were completely away from any of our on-premise tuning or operational workload. The traditional RDBMS was flat out 32 cores for 3,000 TPS, 3,100, and the NeoDB was around 5.2 cores at 80% busy. But you do have to remember you need a transaction engine as well. The transaction engine in this case only had 8 cores, but it did need a good stamp of memory. I think we had 180 GB on there. But the conclusions are that you can, with multiple TEs, multiple SMs, single TEs, single SMs, have linear scalability. You can drive lower latency in the architecture. And obviously, because the licensing is based generally on TCO for what you're using less cores on a NeoDB environment. Although I do not personally have a licensing cost, please contact the NeoDB representative. So it's very well suited to Terminus and banking applications to be ported to the cloud. Thank you. Okay, we're going to talk to you now about Transact, which is the typical T24 updates coming into Terminus T24. So that's Transact, and Infinity. Infinity is part of our product stream, which is an inquirable database. Thanks. Okay, so we needed to run a benchmark. We needed to scale up. We needed to use the cloud. We needed to prove that Terminus and NuoDB can reach dizzy heights. The previous largest benchmarks I've ever been involved with TPS were around 10 to 12,000 TPS. Our board measured this as success criteria as around 50,000 transactions per second, which is a vast number. So we were trying to push the high water benchmark, which is obviously optimized and doesn't have lots of historical data within the actual database itself, although it does have a proportional amount. We benchmarked it. Its scalability was quite excellent. I'm going to go through the benchmark itself. The architecture is all brand new. It's been heavily tested in-house. So you'll see use of modern architecture transact. That's T24 Terminus workload optimized for updates. Data event streaming, which is moving read-only data through microservices into a separate database, which we're in this particular case we're using a holdings API for holding the balances for reading for our inquiries. The good points about it: it's cloud native, it's agnostic characteristics, it allows us to run on anything, and it handles DynamoDB, Kinesis. It will spin out to Cassandra or other operators. It's dynamic deployment, elastic scale, gives us a fantastic TCO because you're only paying for what you're using as you scale up. Thank you. So these are the highlights and the big numbers. So you have 51,000 TPS end to end for transact and infinity. As you can see, the breakdown is 12.7K for TPS for the updates, very heavy transfers. And then you have the lighter inquiries being hit extremely hard at 38,500 TPS on an infinity database. We have to run a close of business. A close of business is mandatory before a bank can settle its arrangements, settle its money for the end of the day. It has an end of day, and we call this a close of business within Terminus. And this settlement procedure effectively opens up and moves all the real money from all the places within the system and settles the day. This is a very large batch process, but we were able to use the auto scaling features within AWS and NuoDB to be able to push up hundreds and hundreds of containers to give us a runtime of 2 hours 34 and 100 million accounts. So the only other point I want to make on that slide is that the latency was low. So if you run an update within transact T24 Terminus, it will be reflected via the streaming platform in under 1.2 seconds. Should you try and execute a transfer and then immediately go and look at your balance, you will see that balance updated. Thank you. Okay, slightly busy slide. I won't go into vast detail, but effectively you have 6 boxes on the screen. Your top left box is your Infinity Holdings. This is the API call count over into the secondary database. The top center is the real transact Terminus workload being run in Kubernetes containers. Now these scaled up to 192 containers for a total of 768 cores, x86 64 cores. So it's a very massive environment. Under the covers, of course, I know that you're now thinking, but you must have had some database cores in place. Database and TE and many others all came together to 336 cores. So this is a very large environment, larger than anything we've tried to push before. We've proven that we can run many hundreds of millions of accounts, but in this case we're running 100 million, and the TPS is the key part to this. We were able to push the transact CPU up, top right hand box, and every time we pushed it up, obviously it would auto scale the next container. As you can see, every container has to linear scale, otherwise they won't start the second and third and fourth. So the throughput TPS for Infinity on the bottom left, 38,000 inquiries per second. This is being hit through Lambda functions. and then you have the TPS for transact itself. Thank you. The breakdown of mix is obviously very different. The workload, banking workload, is going to be very different in this environment to traditional retail. We're trying to do bookings, transfers, and reservations and payments. We've added payments into this from currents to savings and making it as real world as possible. And then balance inquiries and transaction lists. That's listing the recent inquiries that you've had, the recent transactions on your accounts. So you can see that there's a ramp up over time. We tried to push this very hard. We ran this 50,000 TPS over a 1 hour period plus. Incredible amounts of IO were required, but it was totally sustainable, totally linear, and the performance was static. Thank you. So just a quick piece here on the Infinity part. The Infinity Lambda part. So what you're actually doing is you're calling this Infinity Holdings API through the API gateway, and you're doing the API count very, very high, pulling the inquiries from the database. Basically, these are the balance inquiries split across the transaction details. Thank you. So we have a busy slide here. So what we were trying to do is trying to separate the two types of workloads. It's very difficult to do this with any monolithic standard system. We were able to, I think Martin touched on this briefly earlier, we were able to segregate the types of transaction workloads which were flowing through the system, through the TEs and SMs, to be able to give us the throughput, the smooth performance we need. But of course, having the multiple TE, SM requirements in the background, giving us a huge amount of resilience. So from the top AWS cloud part, you can see the load generators fire in from your left. They push into the Amazon MQ and Amazon ECS, and then we start to scale up through Kinetis, through DES. So transact itself is being hit 12,000 times a second with heavy update transactions. And the bottom piece there is Infinity Gateway being hit hard at 38,000. Thank you. Now, as opposed to this huge scale 50,000 TPS benchmark, we can do some things very differently from a traditional deployment model. This customer benchmark, the top box with your web browser, that's how a bank would normally interact with the outside world. Then you have the MQ clusters of transactions coming into the main WebLogic, JBoss tier of VMs, and all these VMs are provisioned. And as you can see here on the box on the right here, you've actually got 18 or 19 physical servers, 480 vCores. So all of these infrastructure is online all the time, standby, waiting for your peaks. It's not running just your operational workload. So when on the previous slide you saw it scale up as the workload came in, scale down as the workload went away, that doesn't happen here. All it does is just scale up the performance on the CPUs and scale down the performance on the CPUs. The cost and TCO is exactly the same. And at the bottom here you see an Exadata cluster, but basically it's a large cluster, 96 cores of our traditional workload on an RDBMS. Those 96 cores would equate to probably 20 cores in a NeoDB environment on a 5-to-1, maybe an 8-to-1, depending on the workload requirements to the SM. So you can see there's a large benefit for running, for a start, in the cloud with NeoDB, and secondly, gives you the flexibility and ability itself to be able to scale up with only the workload that you're paying for, which is obviously paramount to your business. Thank you. Now here's a large cloud benchmark example running from 2017. This one was 25 million accounts, and this is a real customer benchmark. As you can see from the big square box on the left at the bottom, you will see that there are 5 48 core servers running the database services for this enterprise architecture. Now, these are all online in the cloud all the time. They're not scaling up, they're not scaling down. They're just running at cost to support their peak. The response times were also not quite so good, being in this particular space with the database. Huge amount of tuning was required. And still, when you're running 240 cores here, you would probably be running something along the lines of 30 cores to 35 cores of NeoDB in the same space. So a massive saving. And the second box on the right-hand side in front of you is the DR. Now, the DR would certainly not be required in a NeoDB deployment because you would be having 3 nodes already on the left-hand side, so you could just distribute one of those nodes over there. Thank you. Now, this is a little bit of our future, some of the things that are coming along with us. Terminus has been trying to be as flexible as possible in the marketplace, and we've had lots of people asking, can you run on the mainframe? Can you do many other things on the mainframe? Now, we used to have an offering on the mainframe. We no longer have that, but what we do have is Linux One, which runs on IFL's integrated facility for Linux processors within the mainframe itself. So you don't actually have to buy a mainframe. You can buy a mainframe if you wish, or if you already have one, you can provision those processors to run a Linux workload on Red Hat under an integrated facility for Linux processors, which are much, much cheaper and much, much faster than standard processors. So we're something we've been doing. We've done the traditional 50 million account benchmark from the Linux One point of view, all very good, all fully scalable, 62 cores, got us to around 3,000 plus transactions a second, business transactions. But we are now working with our partners at IBM and NeoDB to incorporate the NeoDB testing and auto scaling into the IBM Linux One architecture, which has now been made available in the cloud. So should you want it on premise or should you want it in the future in the cloud, that's something that Terminus and NeoDB can help you with. Next slide, please. Okay, so just to wrap up, we were running 3,000 transact TPS on 62 Linux One cores. I would expect that the 12 that are running the database there could be reduced to probably more than less than 8 if we were running NeoDB, or perhaps even 6. So that's something that's coming for the future, Linux One and NeoDB, because it's excellent way that the mainframe Linux One boxes handle their memory, which is obviously paramount to NeoDB. And that concludes what I have to say. So back over to you, Nick. Thank you very much.
Thanks, Simon. Nick, I can take it from here, guys. I appreciate that. I found that to be extremely informative, and for everybody who's been listening in, we do have some useful resources that are included here in the last slide of the deck. And as we share this deck, you'll have access to it. So we hope you'll certainly give each of these links a look and find some more information on all that we've discussed today. So again, thank you guys. We do have a few minutes left here for questions. So I was thinking maybe we could just jump on a few of these if you're up for it. The first one, Nick, would go to you, and that would be, how do you enforce ACID in a distributed database?
An excellent question, and one that we could take another whole webinar to answer in detail. But the essential parts of it are that we only acknowledge a commit back to the client when we know that we have the multiple copies from the multiple SMs written to disk. We also have each TE broadcasting the changes that it's making to the other TEs. So you can actually consider our TE layer as being a transactionally consistent memory cache. So the notification to the other TEs keep them up to date, and so any request coming to another TE will also see an ACID consistent view of the database. And we enforce consistency first by saying we will only acknowledge a transaction when all of the SMs have acknowledged back to us.
Okay. All right. That makes sense. And Nick, if I could just stay with you quickly, there's another one here. Does scaling up the TEs add any overhead?
Also, an insightful question. Thank you. Yes, you have to have communication between the TEs, so there will be additional messaging between the TEs as you add more TEs. So if you looked at those graphs that both I and Simon were presenting, the lines looked pretty straight. If you zoom in on those, you will see that they will curve down as you add more TEs. We certainly run in tens. On the DBT2 benchmark, we've run 40 TEs. So you can certainly scale up a large number, but you will plateau out at some point where the messaging overhead will start to be visible. Yes.
Okay. Excellent. I appreciate that. Simon, the next question here is for you, and it's around what factors drive the creation of a new benchmark from your team and from Terminus? Why do you guys need a new one? How do you make that decision?
Okay, thank you very much. Another excellent question. There are two real types of benchmarks that we have. One of them is our development product go-to-ready. So that's go-to-market, as we call it, GTM. And the second one is for securing sales. When you're buying a fantastic banking system, it's not going to be cheap. These are enterprise pieces of software that take quite a lot of maintenance, looking after, running around the world to look after these things. So what drives us mostly is the customer requirements for a sales engagement. So for example, we had a bank recently last year say, well, we like Terminus software, yeah, it's all very good, but can you pay 23 million people 10 pesos within 8 hours? It's a very, very strange requirement. So of course, we had a business case, we looked at this, and they said, if you can prove to us that you can do this, this will be a de facto big benefit for the sales process. So there's two types really. The first one is really go to market. Can we get it all scaling correctly as a new product offering? And then there's the actual acid test, as you like, with the bank saying to us, okay, you say it can do it in a lab, come and do it on our environment, or come and do it in the lab for us with our workload.
That makes sense. Yeah. I'm interested. What are some of the challenges that you run into in a benchmark? Anything?
Oh, well, we have many challenges. A lot of the time, it's the customer not quite understanding what they're trying to get out of the benchmark itself. So they will have a requirement, for example, for opening hundreds of millions of accounts or tens of millions of accounts, and you have to speak to them sensibly and say, what is your real future growth, and negotiate how to interpret their idea of their growth to the actual. There's other challenges, of course, around the performance space. Some customers will have very, very simple accounts, things like your bank account perhaps, that gives you no interest, no charges. That's all very good and easy. But others will have charges for deposits, charges for everything for overdrawn, things like this. So we've got a lot of bespoke transactions that we have to work, and every single bank, as I've said before, is different, and that's a big challenge to match their requirements.
Yeah, no, I can imagine it's exciting to see the ways that banks today and in the future are thinking about how do they build for what's to come, and certainly
Absolutely.
an exciting future. So I
believe
appreciate that.
the only way they can build for the future is to see some form of scalability and some form of scale out and scale up ability, which puts us in a good space.
Yeah, no, absolutely. All right, I have one more question here, and Nick, I'm going to come back to you. It has to do with the size of the database. If the database is many gigs in size, doesn't that mean that a replacement SM will take hours to sync before it comes back online? Could you speak to that?
I certainly can. Thank you. Also, an excellent question. So when we bring the SM back online, there are two points in there. The first is that it only needs to synchronize what it missed. So if it was down for 5 minutes, then it's got 5 minutes worth of updates to synchronize. If it was down for an hour or two, then it's got an hour or two to synchronize. So regardless of the database size, the first primary factor is actually how many updates were missed. And the second point is that if you shut a database down, an SM down for a large amount of time, And so the delta between current running state and what the SM has on disk becomes larger than you'd like to handle with straight synchronization. You can precede the synchronization with restoring a backup into there first. So you might have a backup from the previous day. Let's say you might have an SM that was down. The availability zone went down for 2 days or a day, and we can then take a backup from an hour or two ago and load that in first, and then the synchronization of the current state will go from that point. So you're very seldom pushed to have to load the entire state or even a large state. So first of all, for a small outage, just let the standard synchronization go, and then for a large outage, you can have a backup loaded in. And with things like Kubernetes, that can be automated. So the decision can be made automatically in how the SM starts up, that it sees that it's more than an X amount of time out of date and loads the most recent backup and then proceeds with the synchronization. So as part of a SaaS offering, that can all be part of the automated SaaS management of the database.
That makes sense. I appreciate that. And as a father of 2 young ones myself, it's nice to know that I'm not alone in having some helpers as I move through my day-to-day professional world. So
I apologize for the small failure event that we had there. Yes.
No worries. No worries at all. I think we all completely understand. So, gentlemen, I want to thank you both. I think we're going to leave it there. It's been a great session. Thank you for a great presentation. And a big thank you to the audience for attending our session. We hope you found today's webinar informative and useful. We will follow up to any questions that we didn't have a chance to cover. We will be in touch. We will follow up with you. Please feel free to visit newodb.com or terminus.com for more information. Thank you again for attending, and this will conclude today's webinar. Thank you.